All right. So, are we ready? Are we ready? No, but yes? Okay, so today we're going to look at polar derivatives. So, we've got two different ways of looking at it. One is to say dr d theta, which means that you're looking at the rate that the radius is changing with respect to the angle. So how is the radius changing as the angle changes? You're going to be finding the points farthest away from the origin. This will tell whether the radius is decreasing. So if your derivative is smaller than 0, then your radius is decreasing. If it's greater than 0, then your radius is increasing. And it's just a regular derivative, so like first derivative, the rules that we've used in the past. dy dx, at this point, as we hopefully know, this is the rate that y is changing with respect to how x is changing. It's the slope of the tangent line. Good. Since we are given r in terms of theta, if we can rewrite x being in terms of theta and y being in terms of theta, then we're going to say that we can find dy dx by looking at the parametric equation. So if you guys remember, parametric equations have one equation for x equals something, one equation for y equals something. And that something, when we did parametric, it was typically in terms of t. But now that we're in polar, we're going to have the parametric equations are going to be in terms of theta. So you're going to have x of theta, y of theta. Okay? So recall, x equals r cos theta. That's how we're going to find the x for our parametric equation. Y is r sine theta. That's how we're going to find the y for our parametric equation. And that means that when you do your dy dx, you're going to be finding the derivative of y and the derivative of x. And both of those are product rules when you find their derivative. Because you have r cos theta, r times cos, that's product rule. R sine theta, r times sine, that's product rule. Okay? So the formula for finding... the formula for finding the derivative, we're going to say dy dx, that's our notation. But you're literally saying that's like y prime over x prime. So y prime is going to be the derivative of r sine theta. So how do we do that? How do we take the derivative of r sine theta?
R times cos.
Yep, so the first times the derivative of the second plus sine times 1 in this specific case, but it would be r prime, whatever they define r to be. So if r was 5, then you'd say the derivative of 5 is 0. If they gave you an r and they said that r equals tangent, then you'd say the derivative of that is secant squared. So it would depend on what r is. So I'm going to say times r prime. So first times the derivative of the second plus the second times the derivative of the first. So there's the top. And then for the bottom, what would we have? So r times negative sine plus cos times r prime. Okay, so you can kind of do it where maybe you keep this sheet out and think of this as like a formula that you're using and just kind of plug stuff in. You can do it that way. Or you can just think about finding your parametric equations each time, finding your x equation, finding your y equation, and then taking the derivative of those. And that, I think, is probably the best way for you to do it because that might feel familiar to last unit. We did that several times where we took the derivative of y, put it on the top, took the derivative of x, put it on the bottom, right? You remember doing that? Okay. All right, r is differentiable at the point r theta as long as dx d theta. So dx d theta, this is actually saying x prime. That's the derivative of x. As long as that does not equal 0. Why would it be important that that does not equal 0? Because it's on the bottom, that makes it undefined. So as long as it's not undefined at that point, then we can say it's differentiable there. Okay. Horizontal tangent lines have a slope of 0. And so if we think about the slope being defined as dy dx, so if we have dy dx as where our slope comes from, then that means that this part right here equals 0, because to make a fraction equal 0, the top has to equal 0. And so we are going to find our horizontal tangent lines where dy d theta, this is just the y prime, where y prime equals 0. So horizontal tangent lines happen where the derivative of the y equation is 0. And this is as long as dx d theta, or the bottom, does not equal 0. So only the top equals 0. You can't say the top equals 0 and the bottom equals 0. It has to only be the top. All right, what's the slope of a vertical tangent line? Undefined. So that means in dy dx, the denominator is going to equal 0, because that's how you take a fraction and make it undefined. And so that means that dx d theta, which is the same thing as x prime, that means that your dx d theta equals 0. And dy d theta has to not be 0 for this to work. So only the bottom equals 0, not the top and the bottom. And then we have a special note. If the top and the bottom equal 0 at the same time, you have no conclusion. It's not a vertical tangent line. It's not a horizontal tangent line. It actually means there's a sharp corner or a cusp right there. You guys remember what those look like? Yeah, it's not a smooth curve. It's a point. It's a point in the graph. So no vertical tangent line, no horizontal tangent line. That means that every time we are looking for horizontal tangent lines and vertical tangent lines, we're always going to be careful to make sure we don't find one answer that appears to be working for vertical and horizontal, because if that one answer works for both, that actually means it's a cusp. It doesn't mean you have a tangent line there. It means you have a cusp there. All right, we good on that page so far? Okay. All right, go ahead and turn the page. We're going to move on to our example problems. Oh gosh. So I made these packets on the crappy copy machine, and sometimes it skips a page, and I happen to have one that skipped a page. So you should have that front page, and then you should have examples 1, 2, 3, and 4. You guys want to check your packets and just make sure you have them all? Okay. It looks like I got maybe the only packet that didn't get it. It's usually you. Who had it last? Miles had one once where it didn't have a page. Yeah. All right. So there's example 1. It says find dy dx, and it gives you that your r is 2 cos theta. So that means that for us to write this as a parametric equation, we know that the formula for x is r times cos theta, and the formula for y is r times sine theta. So you have 2 options for doing these problems. You can either look at the front of your packet and treat this like a formula and plug it all in and solve it. Or you can find your x and find your y and just do y prime divided by x prime. Okay? And that's what I'm going to do, because I don't like to make you guys memorize formulas that you don't need to memorize. I'd rather have you guys just understand how it works. So to find x, we're going to say x is r, which is 2 plus cos theta, times cos theta. And so what does that give us for the x parametric equation? Okay. And then y would be r times sine theta. So what would that give us? cos theta sine theta. So now to find the derivative, dy dx, we have to do y prime divided by x prime. So the derivative of y would be 2 cos theta. So the first part is pretty easy. And then what do you have to be careful of right here? Product rule. So first times the derivative of the second. And I don't know about you guys, but I found for me, I like to put my product rule in parentheses to know that it like represents a term. In this problem, it won't matter because you have a plus sign right there, but sometimes you're subtracting a product rule, and for me, that helps me remember to distribute my negative. So I'm going to go ahead and just put the parentheses there, even though in this particular problem they're not super necessary. So I did first times the derivative of the second plus the second times the derivative of the first, which is theta sine. Okay, so there's our y prime. And then we have x prime on the bottom. So the derivative of 2 cos theta would be negative 2 sine theta plus, and then this I'm going to think of as being cos theta squared. You could do it as cos times cos if you wanted to do a product rule. Or you could do it as cos squared if you want to do the chain rule. Yeah. So bring the 2 to the front. So 2 times cos theta to the 1 power times, so there's our chain rule. We did the derivative of the outside times the derivative of the inside. Negative sine theta. Okay. So now to get my final answer, I just have to kind of clean things up a bit. So that gives me 2 cos theta on the top, and then what else do I have? And what do we have on the bottom?
Negative 2 sine theta. Minus 2 cos. Cos theta sine theta.
And one thing, I don't know, there's so many different ways to write derivatives, like there's so many different types of notation. I did notice on the parametric test that some of you guys, you're good at seeing that y prime and x prime are derivatives, but you didn't notice that on the parametric test that dy dt was the same thing as y prime, and dx dt was the same thing as x prime. So if you think you might forget that, that could be a good thing to write on your notes, is that dx d theta is the same thing as x prime, and dy d theta is the same thing as y prime, just to make sure in case a problem happens to use the other notation that you still know what it means. Because that, on the parametric test, that did mess up some people. All right. How do we feel about example 1? Ugly but doable? Yeah. Okay. Number 2.
That's it.
That's it. That's all it wanted was the derivative, dy dx, and so that's how we do it. Okay, number 2 says find the points where the horizontal and vertical tangent lines occur. So what are we looking for a horizontal tangent line? Yeah, x prime is going to equal 0. Oh, no, that's the bottom. We want the top to equal 0. Y prime. Y prime is going to equal 0. What about the vertical tangent? X prime is going to equal 0. All right. So they said that r is sine theta. So if we want to find, and they told us that we're looking for this on the interval 0 pi, you want to be specific because we know that these sine curves, cosine curves, this sort of thing, they're like cyclic, right? Like they go up, down, up, down, up, down. So if they don't tell you an interval to look for the answers on, then you have to do like every single answer, and they repeat infinitely many times. So pay attention to your interval because it's going to tell you should I have 2 answers or 4 answers or 27 answers or whatever. That make sense? Interval is important because it tells you how much of the unit circle to look at. So if we look for x, we know that x is r times cos theta. So what is our parametric equation for x this time? Yeah, sine theta times cos theta. All right, and then y is r times sine theta. So what is our y parametric equation? Yeah, sine theta times sine theta. So I'm going to call that sine squared.
What are you doing?
Me.
All right, or if you want to think of this to make it easier for you to take the derivative, if you want to think of this as sine theta on the inside and squared on the outside, you can think of it like that. All right. Now, we don't have to write it as dy dx, but I'm going to go ahead and do that because I want to make sure that I keep remembering that the top of the fraction equaling 0 is what makes the slope of 0, and the bottom of the fraction equaling 0 is what makes the slope that's undefined. So I want to make sure in my head that I'm understanding where these things come from. So dy dx, I have the derivative of y on the top. So what's the derivative of y? So we did the derivative of the outside times the derivative of the inside. And then how about the derivative of x? So first times the derivative of the second plus the second times the derivative of the first. So what math should I do now if I want to find the points where there is a horizontal tangent line? Yeah, so take the top, make it equal 0. So 2 sine theta cos theta equals 0. And I'm solving for theta. Does anyone have an idea of how I solve for theta? You could divide the 2 over, right? Yeah, you're kind of factoring basically. So I'm going to think of this as like, well, I could go ahead and divide the 2. We know the 2 is not going to make any difference, right? Because it's 2 times something equals 0. So really you can think of it as like this is one of your factors and this is another one of your factors. And so I'm going to say that sine theta equals 0 and cos theta equals 0. So I have to picture on the unit circle where the y coordinates equal 0 and where the x coordinates equal 0. Not at the same time, just anywhere.
0 by
So I've got 0, right? That's a y coordinate equaling 0, so that's one of the solutions over here. Here's another place where the y coordinate equals 0, so 0 and pi are 2 of the answers. And then the x coordinate equals 0 up here at pi halves, and down here at 3 pi halves, but I am not going to write 3 pi halves. Why not? It's not on the interval. Okay. So there are potentially 3 points where we have a horizontal tangent line. Why am I not writing the answers for my horizontal tangent line yet?
Because you don't know where the button.
You need a lot of bottoms.
Yeah, I want to make sure I don't have 0 on the top and the bottom at the same time. Because what happens if it's 0 on the top and the bottom at the same time? Then it's a cusp or a sharp corner. It's not actually a tangent line. Okay, so since I haven't checked the vertical, I'm going to leave this here for a second. Let's go ahead and do vertical. So this is where we're going to take the denominator and make it equal 0. So So negative sine squared plus cos squared equals 0. This one doesn't work very well for factoring.
But it's a no, it's not.
Yeah, it's not bad. It's okay the way it is. What I'm actually going to walk you through how we would solve this one, and you'll probably be like, oh, I might not have seen that, but it makes sense. We're going to go ahead and take this chunk, and we're just going to add it to the other side. So we're going to say cos squared equals sine squared. And then we're going to square root each side. And what happens when I square root something? What else do you normally put in front when you square root? Plus minus. So plus minus cos equals plus minus sine. So because of the squareds in this problem, it doesn't matter if the number for cos or sine is positive or negative, because we would have been squaring it. We would have forced it to be positive anyway. So this is basically saying, where on the unit circle do you see an x coordinate and a y coordinate that are the same number, but the signs don't matter? 5/4? Mm-hmm. So right here at 5/4, because that's root 2 over 2 and root 2 over 2, so they're the same sign there. And then where else do we see that? 3 5/4, yeah. So that's right over here. That's negative root 2 over 2 and then positive root 2 over 2. Again, the signs don't matter because ultimately when we plug these in, we're squaring the numbers. That's why they don't really matter. So the two places where this happens is at 5/4 and 3 5/4. Okay, so based on our answers, is there any point where we are expecting to see a sharp corner or a cusp? No, there's none of those answers overlap. So that means that these are 3 answers that we're going to have for the horizontal tangent line, 2 answers that we have for the vertical tangent line. Now, we are writing these coordinates, these points, as polar coordinates. That means we're going to have an r value and a theta, and we definitely already have the theta. So if you look back at the instructions to the problem, how do you think you're going to get your r value?
Plug it back in.
Yeah, plug it back in up here. It says r equals sine theta. Okay. So to find our first point, we're going to say r equals sine of 0. What is sine of 0? 0. So that gives you the point 0, 0. Our next point, we're going to plug in pi. So r equals sine of pi. What do you get when you plug in sine of pi? You get 0 again. So the r value is 0, the theta value is pi. And then the last one is when theta is pi halves. And that would give you a 1. So that's 1 pi halves. So if we were to graph r equals sine theta in our calculator, we would expect to see horizontal tangent lines at 0, 0, 0 pi, and 1 pi halves. Shall we check it to make sure that makes sense? So r equals sine x. My window is going to go from 0 to pi, because that's the only interval we have. And I can see a horizontal tangent at 0, 0. And you can actually see your horizontal tangent at 0, 0 and 0 pi is actually the same tangent.
Mm-hmm.
Do you guys see that? That's kind of like the bottom of the circle. It's like the bottom of the circle at this side, the bottom of the circle at that side. And then the other one is at 1 pi halves, which is up here. So basically we have 2 horizontal tangent lines. Does that make sense?
Yeah.
Okay. All right. Next one. So here we're going to find our vertical tangent lines. We've got r equals sine of pi fourths, which is root 2 over 2. So that point is going to be root 2 over 2 pi fourths. And then the other one is r equals sine of 3 pi fourths, which is same thing, also root 2 over 2. So root 2 over 2, 3 pi fourths. And so our vertical tangents are over on these sides. Yeah. Interesting? Yes? No?
Yeah.
Interesting.
Can we make this shape?
Draw a little
I wanna
picture if
make
you
a
want.
shape.
Why are you so obsessed with that shape?
What shape? You could play with things until you figure out how to make that shape. All right, number 3.
I'll make the most elaborate.
Example 3 is exactly like example 2. It's just a different R value. So can you guys talk me through it? What should we do first?
First, gotta find you gotta do y dx.
X equals R cos theta.
Yeah.
Y equals R sin theta.
Right now my R is written as a factor. 2 times 1 minus cos. So I'm going to go ahead and distribute that 2 to start with. I don't want to have like extra product rules in there if I can avoid it. Okay. So you guys said we write our X and our Y first?
So it's gonna be the R. It's gonna be the R cos.
So R times cos, R times sine, that was a pretty good like whole class knows goes situation.
I was in the process
I was
of like
already
being
stuck
in my
on
notes
it.
anyway.
Nobody there?
Me? Today? Yeah. I mean, if you, yeah.
So what'd you guys get for X?
Two cos minus 2 cos squared.
And then what'd you guys get for Y?
2 sine theta minus 2 cosine theta.
Okay. I already don't like this one.
That's good. It looks good.
So for dy dx, what are we going to have on the top?
Two cos.
And now we got a product rule, right?
Yeah.
Do you guys want to include the 2 in the product rule, or do you want to leave it in the front? Leave it in the front? Okay, so minus 2, and now we're going to do our product rule. Okay, so we got first times the derivative of the second.
Cos.
So cos times cos
Cos squared.
plus the second times the derivative of the first. Okay.
That looks like a trick idea, right?
Almost. They keep being cos squared and sine squared, but a minus in there.
Yeah.
It's got to be a plus to be a trig identity.
Rats.
Yeah. But even with the negative, it's still going to make your sign the opposite. All right. Derivative of x.
2 negative 2.
And then up here, I'm going to think of this as negative 2 times cos theta squared. Okay. And then what do we have up here?
What?
74 cos.
So the first times the derivative of the inside.
Negative
Minus.
Okay.
because the chain rule is already 2 parts.
Yeah, I wrote it so I could do the chain rule on it. Okay. So on the top, we have 2 cos theta minus 2 cos squared. And then we've got a negative times a negative. So plus 2 sine squared. Over.
I hate this.
Plus 4 cos sine.
Yeah. Sorry I wrote that silly like. I was trying to conserve space.
I'd rather be doing calculus with letters than doing this.
All right. You guys ready for this?
Done.
Alrighty.
I don't know what to do next. Wait,
So, think back to example 2. What do I do next? Okay, so we're going to look for the horizontal tangents.
you gotta do the top.
Make the top equal 0. So 2 cos theta minus 2 cos squared theta plus 2 sine squared theta equals 0. That's that's kind of hard to solve, right? Okay. If this part wasn't there, then I would say we could just move one of the squares over the other side and kind of do what we did on example 1. But that cos is there. So our method of solving this one is going to be to make the entire problem in terms of cos, because then we can factor it, and cos theta will be like the variable that we're factoring. Okay. So that means this sine squared we don't want anymore. You guys remember your trig identities? Yeah. It's not 1 plus, 1 minus. Yeah, so I'm going to take the sine squared, and I'm going to replace it with a 1 minus cos squared. And that's one of the trig identities. All right.
Now you take the. Now you do the. You substitution.
You don't need to do U substitution because you're not integrating.
James, stop trying to do too much.
So I'm gonna go ahead and distribute that too. So what do I have?
2 minus 2 cos squared.
I actually can still do this.
Okay. So now if I think about the whole problem, I have negative 4 cos squared. You guys see it? Because I've got negative 2 right here and another negative 2 right here. Okay, so negative 4 cos squared. And then I have 2 cos. Plus 2 equals 0. Let me get, okay, so this is like we are factoring. I'm going to write it off to the side. We are factoring negative 4x squared plus 2x plus 2. That's what we're factoring. We just have coses instead of x's. Okay. So if you saw a problem like this, what would you do? Take out a GCF of
2.
and take the negative out as well. Negative 2. So that would leave you with 2x squared minus x minus 1.
Squared minus.
That's a good question.
Okay.
And then we would know that if we were factoring this, we'd have one set of parentheses with a 2x and the other would have an x, right? And then somehow these two numbers on the end would have to multiply to be negative 1. So one of them has to be a plus 1, one of them has to be a minus 1. So where do you guys want to put the plus? Where do you want to put the minus?
One of those.
Plus 1 here?
You pick.
So we can just check to see if it works. So we got 2x squared minus 2x plus 1x minus 1. So this is the one we want?
Yeah.
Okay. And if you guys were solving this problem, what would you say?
X equals 1/2. X equals -1/2. X equals 4.
There we go. Okay. So here we're going to say cos theta equals -1/2. Cos theta equals +1. Okay. Now, for this problem, we do have to solve for theta. So now we got to picture our unit circle. And they told us that we're using the interval 0 to 2 pi, so we're using the entire unit circle. And they're saying, where is the x coordinate -1/2? Pi thirds would be +1/2 because that's to the right.
Oh, crap.
So where do you go left?
So
2 pi thirds and 4 pi thirds. So
I was close.
theta equals 2 pi thirds and 4 pi thirds. And then here they're saying, where is the x value just 1? At 0, right? 0 and 2 pi, I guess, since we're including 0 and 2 pi. So theta equals 0 and 2 pi.
What?
Okay. That was our horizontal. That was the tough one. Does that make you feel better? We did the tough one first?
We're not done.
We're not done, but the vertical one is better. There's more. There's more.
more room. But wait, there's
Did you guys see why I was conserving some space at the beginning? The good news is you can just say, go on the back.
The good news is there's no test for this one.
There's a test.
Yeah, what are you talking about?
Yeah, what are you talking about? All right. What do we have to do for vertical? Set the bottom equal to 0. So -2 sine theta plus 4 cos theta sine theta. And the nice thing about this one is it's pretty easy to factor. This is like if you were factoring -2y plus 4xy. You could take out a y, and what else could you take out? And what would it leave you with? Okay. So we're going to take out a -2 and sine theta, because that's kind of like our y. And that's going to leave us with 1 minus 2 cos theta. Okay? And if you were to solve this, you would say y equals 0. And what would you say for this one?
Yeah, I have no clue. X equals.
It'd be 1/2, yeah. Because if you were to do it by hand, you'd be like 1 minus 2x equals 0. And minus the 1 over, and then divide by -2. Yeah, it's not quite the same as the ones you guys are used to, but it's still.
So we gotta solve for theta too.
And then, but yeah, we're gonna have to solve for theta. So cos theta is 1/2. So here we're asking what values of theta, what angles have a y coordinate of 0. Where do we see a y coordinate of 0?
0, pi, 2 pi.
Okay. And then where do we see an x coordinate of 1/2?
There's 7. No, 5.
Okay. All right. Do we see any places where we would have a sharp corner or a cusp?
0, 2 pi. Yeah.
Not pi thirds, because this is 2 pi thirds, 4 pi thirds, and then pi thirds, 5 pi thirds. So we got a lot of thirds in there, but none of them are.
The same.
Okay. So at least we got to cut out some of them, though. We got
Ricky
to
the
avoid
third.
some of them. Okay, now what do we do?
You finish, go to the next problem.
No, we're not done. We're not done.
Oh,
Yeah, you plug it
Oh
in.
my God.
Because what's the big picture? What was our goal here? To find points. We wanted to find points. Points are in terms of r and theta. We already have the theta, we need the r. So we go back, how do we find r? Yeah, you can plug it in here if you want, or you can plug it in here. So for our horizontal tangent, we're going to say r equals 2 minus 2 times cos of 2 pi thirds. Cos of 2 pi thirds, we already know it was negative 1/2.
Yeah, so 2 minus.
So 2 minus 2, the 2 is being times, multiplied by negative 1/2. 3. So that's the point 3, 2 pi thirds, sorry. And then the other one is 2 minus 2 times cos of 4 pi thirds. Luckily that still equals 1/2, negative 1/2, and so that's the same.
Good job.
Okay, so there's the points where we have our horizontal tangent.
So there's more.
And then our vertical tangent. I didn't really leave room for this.
It's okay.
Oh, I thought we could insert.
So we've got r equals 2 minus 2, and then we had 3. We've got pi thirds, and 5 pi thirds. I'm writing sideways.
Either just wrote at the top of the little space and go to the problem.
I'm going to say,
I already wrote it down.
I'm going crazy.
okay. So r equals 2 minus 2 cos 0.
Wait, I thought we weren't plugging in zero.
Cos pi. So when you plug in pi, what's cos of pi? Negative 1. Negative 1. So 2 minus 2 times negative 1 is 2 plus 2, so that's 4. So that gives us the point 4 pi. And then we have r equals 2 minus 2 cos pi thirds. We know that cos of pi thirds was 1/2. So 2 minus 2 times 1/2. 2 is 1. And then 5 pi thirds is the same. It's also going to give you 1/2. But wasn't that fun?
No.
No.
Rude. You guys are so rude.
Honest and rude.
Okay, so big picture. Big picture. What's the process for these problems? If you think big picture, what's the overall process? What do we do first?
Substitute r.
Yeah, you write down your parametric equation, right? What your x is, what your y is.
Okay, and then you get dy dx doing the product rule.
Yeah, so then we find the derivative, dy dx, and we're probably going to have to use the product rule somewhere in
And
there.
then you clean it up, and then you take it down and set it equals 0.
Yeah, so the
You
top
want
of the fraction
horizontal.
equals 0 for horizontal,
And then vertical.
And
and the
basically-
bottom of the fraction equals 0
and
for
basically solve
vertical.
to get
You do a
0.
bunch of stuff.
And then you take those theta values and you plug them in to find your r values that correspond to them. Okay. One last example. This one's better. It doesn't take as much space. Yeah, I should have moved it down more. It doesn't take as much space. All right. It says find the tangent lines at the pole. Where's the pole? 0, 0. So, well, actually, it's 0 and then any theta. It doesn't matter. But we do know that the r value is definitely 0 at the pole. All right. So we're going to take the r and set it equal to 0. We're going to say 0 equals 2 cos 3 theta. So I set r equal to 0 because it told me that we were looking at the pole. So I already know the r coordinate of the tangent, the point that the tangent line is happening at. I already know that the r coordinate is 0. So now I just have to find what my theta is going to be. So I'm going to go ahead and divide the 2 over. So that gives me 0 equals cos of 3 theta. Now I know that my original, it says the interval is from 0 to pi. So I know that if I was doing just plain old theta in the problem, I know that that would be between 0 and pi, but we have a 3 theta in the problem. So that's going to be between 0 and 3 pi. So it just means we have to look at a little bit more than the unit circle because of that multiplying theta by 3. So if we think about the unit circle but going a little bit further, where are we going to find x coordinates of 0? Pi halves. 3 pi halves, then we got to keep going because we're going to 3 theta, not just 2 theta. What's the next one in the pattern? 5 pi halves. Okay. So if we picture our unit circle right here, we've got 0, pi, 2 pi, 3 pi. Then you'd say that the x coordinate is 0 at pi halves, 3 pi halves, 5 pi halves, and we're done. Does that make sense?
If you say so.
So we said this is pi halves, this is 3 pi halves, and I just had to find the angle that is coterminal with pi halves because I need it to go a little bit bigger. Okay, I want to solve for theta. How do I solve for theta? How do you get rid of 3? Divide by 3.
Okay.
Oh.
I thought that was like an easy question.
So that means theta is, the first one would be pi over 6. 2 times 3 is 6. So pi over 6.
3 pi over.
And then 3 pi over 6, which you're right is pi halves. And then 5 pi over 6. So those are our 3 thetas.
It's probably not.
Okay, now we have to think back to our to what we wrote here. We said that r is differentiable at the point as long as the derivative of x does not equal 0 at that specific point. Right? That's what we said. So we'll have a tangent. I'm going to write this down.
This is our pole.
We're going to have a tangent line wherever r equals 0. We just found 3 places where r equals 0. As long as r prime of theta does not equal 0. And that's because of the definition of where things are differentiable. Okay. So if r equals 2 cos 3 theta, then what is r prime? It's a chain rule, right? So the derivative of the outside, derivative of 2 cos is negative 2 sine of 3 theta, and then we have to multiply by the derivative of the inside times 3. Okay, so r prime is negative 6 sine of 3 theta. Okay, so what we have to do is we just have to check each of these 3 locations where we think that point might be, and we have to make sure the derivative does not equal 0 at any of those points. So I'm going to say, as long as r prime of negative 6 times sine of 3 times pi 6 has to not equal 0, 3 times pi halves has to not equal 0. And times 5 pi 6. And you can go ahead and type those in a calculator. We just want to make sure they don't equal 0. Am I typing them for you guys?
No, so
I mean,
Yes.
that would be awesome. It'd be great for
your brain's better than me, probably.
Great. So the first one equals negative 6, so it does not equal 0. That's all I care about. The second one equals positive 6, which is not 0. That's all I care about. And then the third one equals negative 6, which is not 0. That's all I care about. So since none of them equal 0, we are good to go. We can say that these are the tangent lines. Now think about it. The tangent line has an R value of 0. That means it goes through the pole. These are tangent lines. So the tangent line is at the angle pi 6, and it goes through the pole. So how do we write the equation of that line? Think back to yesterday. Yeah, theta is pi 6. How do we write the tangent line for the next one? Theta equals pi halves. How do we write the tangent line for the third one?
Some of it is because they're bored.
So is it always gonna be like that simple? We just have to write theta equals.
Yeah, that's because it went through the pole. If it didn't go through the pole, it's going to be a little bit more complicated because it would have a different like y-intercept. That means that if you look back at your notes from yesterday, I gave you guys some examples of what equations look like when they're straight lines, but they don't go through the pole. But the ones that do go through the pole are always that simple. It's just theta equals whatever the angle is of the line. All right, we done.
If you-
Woohoo!